So we will now look at divisibility. So if n and d are integers, we say that n is divisible by d, which is expressed d, a vertical line n, which is read as d divides n, if and only if there exists an integer k such that n is equal to dk and d is not equal to 0. We also say that n is a multiple of d is a factor of n, d is a divisor of n, and d divides n. So these are all the same way of saying n is divisible by d. So let's look at some examples. So 21 is divisible by 3, since we can write 21 as 3 times 7. 5 divides 40, since we can write 40 as 5 times 8. 7 divides 42, since we can write 42 as 7 times 6. 32 is a multiple of negative 16, since we can write 32 as negative 16 times negative 2. 6 is a factor of 54, since 54 can be written as 6 times 9. And 7 is a factor of negative 7, since negative 7 is equal to 7 times negative 1. Now, for any non-zero integer k, we'd be able to write 0 as 0 times k, right? 0 times anything is 0. And so k divides 0. So any non-zero integer k divides 0, which is to say 0 is divisible by every non-zero integer. So for all integers a and b, if a and b are positive and a divides b, then a is less than or equal to b. So we're now going to prove this, and once again, anything that is in blue text will typically be left out of formal proofs. I'm including them just for context. So we let a and b be positive integers such that a divides b. What we will show is that a is less than or equal to b. So by definition, since a divides b, there must exist an integer k such that b is equal to ak. Now, since b is greater than 0 and a is greater than 0, we must have k being greater than 0. Right? This is because the only way to get a positive integer via product is to either multiply two positives together or two negatives together. But since a is positive, k must also be positive to guarantee b being positive. So since k is an integer and it must be greater than 0, then k must at least be positive 1. So a would have to be less than or equal to k times a, but k times a is equal to b. Therefore, a is less than or equal to b, which was as we desired. And so the proof is complete. The only divisors of 1 are 1 and negative 1. So since 1 times 1 is equal to 1, and negative 1 times negative 1 is equal to 1, we know that both 1 and minus 1 are divisors of 1. What we must do now is have to show that they are the only possible divisors of 1. So let's suppose that m is an integer that divides 1. Then by definition, we must have an integer n such that 1 is equal to m times n. So we must have either m being greater than 0 and n being greater than 0, or m being less than 0 and n being less than 0. Right? Again, the only way to get a positive number via product is to multiply two positives together, which is this case, or two negatives together, which is this case. This is a classic division into cases problem. So we first will consider this case here where both are positive. Then m is a positive integer divisor of 1, which means m must be less than or equal to 1 by the previous theorem. However, the only integer less than or equal to 1 that's positive is 1. So m has to equal 1. Now we're going to go and consider this case, where they're both negative. We can write negative m times negative n is m times n, which equals 1. In this case, negative m is a positive integer divisor of 1. So negative m has to be 1, which means that m would have to be negative 1. Now, the reason negative m is a positive integer divisor, right? Remember, we're assuming m is negative. So negative is a double negative, makes it positive. Well, there, in both cases, we have just shown that it's either 1 or negative 1. So the only divisors of 1 are 1 and negative 1. And so the proof is complete. Now, let's look at this. If a and b are integers, is 3a plus 3b divisible by 3? So let's go ahead and take a look. So let's suppose that a and b are integers. Right? This means that 3a and 3b would be integers because it's the product of integers. And this would mean that 3a plus 3b must be an integer because it is the sum of integers. Furthermore, we can write 3a plus 3b as 3 times a plus b. But now a and b are both integers, so a plus b must also be an integer. So look what we just did. We just wrote 3a plus 3b as 3 times some integer q, which by definition means that 3 must divide 3a plus 3b. So yes, 3a plus 3b is divisible by 3. Now, if k and m are integers, is 10km divisible by 5? Right, well again, let's suppose that k and m are given integers. Then we already know that 10km is an integer. It is a product of integers. Now, we can write 10km as 5 times 2km, and 2km is the product of integers, so it is an integer. So we just wrote 10km as 5 times an integer q, which means by definition 5 must divide 10km. So yes, 10km is divisible by 5. So does 4 divide 15? Well, let's suppose that it does. then by definition there would have to be an integer q such that 15 is equal to 4 times q. So this would mean that q would have to be 15 divided by 4, 15 over 4, which is not an integer. So we've just said that q is an integer, and q is not an integer. I'm sorry, that should be a not. This is a contradiction. So this means that our original supposition is incorrect, and we can therefore conclude that 4 does not divide 15. Well, with this, with now the definition of divisibility, we have a new way to define a prime number. So an integer n is greater than 1 is prime if and only if its only positive integer divisors are 1 and itself. So look at another property. For all integers a, b, and c, if a divides b and b divides c, then a divides c. Okay? So let a, b, and c be integers such that a divides b and b divides c. We want to show that a divides c. Okay? So by definition, there must exist two integers, q1 and q2, such that b is equal to a times q1. That's because of a divides b. And c must equal b times q2. That is by b divides c. So if we use substitution, we'll get c, which is bq2, but b is aq1, so we get aq1 times q2. And we can use the associativity property of multiplication of real numbers as a times q1, q2. Right, however, this is an integer because it is the product of integers. So we just wrote c as a times some integer q. So by definition, this means that a divides c. This is what we wanted to prove, and so the proof is now complete. So any integer n greater than 1 is divisible by a prime number. So we let n be an integer such that it is greater than 1. We want to show that there is a prime number p such that p divides n. Now, if n is already a prime number, then we're done, right? Because n divides itself. So let's suppose n is not prime. Then there must exist two integers r0 and s0, with one being less than r0 less than n, and one being less than s0 less than n, such that n is r0 times s0. And this is by definition of composite numbers. Well, then r0 must divide n. Now, if r0 is prime, we're done. We found our prime. Well, instead, let's suppose that r0 is not prime. Then there has to be integers r1 and s1 with 1 less than r1 less than r0, and 1 less than s1 less than r0, such that r0 is equal to r1 times s1. Again, this is by definition of composite numbers. Well, then this means that r1 divides r0. However, by the previous theorem, which is the transitivity property for divisibility, r1 must also divide n, right? Because r1 divides r0, but we've shown above that r0 divides n. Now, if R1 is prime, we're done. If R1 is not prime, then we may continue as we did previously. So we can continue this step. We can find integers R2 and S2 such that R1 is R2, S2, so on and so forth, until we find a prime factor. Now, we must succeed in this in a finite number of steps, because each new factor is both less than the previous one, which is itself less than n, and greater than 1. And there are fewer than n integers that are strictly between 1 and n. Right, this only works because we're only considering integers. If we weren't considering integers, we were considering like rational numbers or real numbers, then there would be an infinite number of values between 1 and n. So what we've done is we obtained a sequence, R0, R1 up to Rk, where k is some integer greater than or equal to 0, and 1 is less than Rk, which is less than Rk minus 1, yada yada yada, less than R1, less than R0, less than n, right? So it's a decreasing, or I'm sorry, in this case the way it's written, it's an increasing sequence. So Rk would be the smallest integer, R0 would be the greatest integer, and all of them must lie strictly between 1 and n. Furthermore, by the process, we know that for each of these values, these r's, each one divides n. So we terminate this process once Rk is prime, however many steps it takes. So Rk is a prime that divides n, which was to be shown, and the proof is complete. So now we're going to look at a typical true or false question. So in mathematics, if you're asked true or false, it is not just, oh, it's true and you move on, or oh, it's false and you move on. It's, if it's true, prove the statement. If it's false, provide a counterexample to disprove it. So here's the statement we want to determine whether it's true or false. For all integers a and b, if a divides b and b divides a, then a is equal to b. Right, so let's look at this, do a little bit of work. So first, we ask, what does it mean for a divides b? Well, this means that there exists some integer q1 such that b is equal to a times q1. Well, if we take q1 to be negative 1, then we'd have b is equal to negative a. Well, oh dear. We were supposed to have a is equal to b, and here we have b is equal to negative a. Okay. But remember, b also has to divide a, right? So in here, I forgot to include that q1 is an integer. Right. So we now look at b dividing a. This means that there has to be an integer q2 such that a is equal to b times q2. Well, once again, if we take q2 to be negative 1, then a would be equal to negative b. And once again, we have that a and b are not equal. So it would appear that this statement is false. And a good counterexample would be to take a to be any integer and let b be its negative. So let a equal 28 and b equal negative 28. Well then, a must divide b, because we have negative 28 is equal to 28 times minus 1. And we also have b divides a, because 28 is equal to negative 28 also times negative 1. However, b does not equal a. So therefore, the statement is false. Now, we will look at one of the most important theorems in all of mathematics, and it is known as the fundamental theorem of arithmetic. And what this theorem says is, given any integer n greater than 1, there exists a positive integer k, distinct prime numbers p1, p2 through pk, and positive integers e1, e2 through ek, such n is equal to p1 to the e1 times p2 to the e2 times yada 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 times pk to the ek, and any other expression for n as a product of prime numbers is identical to this, except perhaps for the order in which the factors are written. We will prove this later. We don't have all of the tools to prove it just yet. But if we look at this, what this theorem is saying is that every integer greater than 1 will have a unique prime factorization. Which we define now. Given any integer greater than 1, the prime factorization, also known as the standard factored form of n, is an expression of this form, where k is a positive integer, all of the p's are prime numbers, and all of the e's are positive integers. And it's written in an ascending order. So p1 would be the smallest prime number, p2 would be the second smallest, so on and so forth, and pk would be the largest. Right, so remember, the previous theorem said that this would be unique for perhaps the order in which the factors are written. So if we just now strictly say that we have to write it in the ascending order of primes, we now guarantee it is unique. So every integer greater than 1 has a way to be written as a product of prime numbers, and it's only one possible way of writing it. Now, this is useful in the study of number theory. For instance, if we're looking for the greatest common factor or the least common multiple of integers, that is easily determined by writing each integer in prime factor form. Now, sadly, we will not be looking at that in the course. However, if that's something you might be interested in, look up a standard course in elementary number theory. So we're now going to go ahead and write the prime factorization for 3300. Okay, so to do this, let's write the factor tree for 3300. Now remember, we know that such a prime factorization will exist. Well, we can write 3300 as 100 times 33, right? Now 100 can be written We can write it as 10 times 10. And of course, 10 is 2 times 5. Now 33 can be written as 3 times 11. And the goal is you want to go until we have all prime numbers. And all of these are prime numbers. So the prime factorization of 3300. Start with the smallest prime you see. Well, the smallest prime we see is 2. And how many do we see in the tree? Well, 1, 2. So 2 squared. Times. Next, we look for the next smallest. Well, the next smallest would be 3. And there's only one of them. Now the next smallest is 5. And we see 2 of them. The next smallest is 11. And there's only one of them. And we see no other primes. So the prime factorization of 3300 is 2 squared times 3 times 5 squared times 11. Now let's suppose that m is an integer such that 8 times 7 times 6 times 4 times 3 times 2 times m is equal to 17 times 16 times 15 times 14 times 13 times 12 times 11 times 10. Does 17 divide n? Well, what we're going to do is we're going to let this piece here be a, and then we will let this piece here be b, now, since we know that a is equal to b, they must have the same prime factorization. Because the prime factorization is unique. Now, because 17 is already prime, and 17 is not a factor of 8, 7, 6, 5, 4, 3, 2, it must be a factor of m. So therefore, 17 must divide m. And now we're going to look at one of the most consequential results of integers, and that is the Quotient-Remainder Theorem. So the Quotient-Remainder Theorem states that if we are given any integer n and any positive integer d, there must exist unique integers q and r, such that n is d times q plus r, and 0 is less than or equal to r, which is less than d. The integer d is called the divisor, the integer q is called the quotient, and the integer r is called the remainder. Now again, we don't quite have all the tools necessary to prove this theorem, So a complete proof will be looked at later. So for each of the following values of n and d, what we're going to do is find integers q and r so that we can write it as n equals dq plus r. And we must, of course, remember that r has to be between 0 and d. So the first pair we're going to look at is n is 54 and d is 4. So if we look at this, and we go, okay, well, let's put 4 into 54. What'll happen? Well, 4 goes into 5 one time. We're left with 1. If we bring down this 4, we have 14. So 4 goes into 14 3 times. We have 2, and 4 does not go into 2. So you should remember from basic elementary arithmetic that 4 goes into 54 13 times with a remainder of 2. What this means is that we can write 54 as 4 times 13 plus 2. So this 13 is our q, this r is our 2. So we'd have q is equal to 13, r is equal to 2. Next up, let's look at now n is negative 54. Well, from the previous slide, we'd have 4 times negative 13 would be negative 52. Well, we want negative 54. So what we're going to have to do is we're going to have to up this, right? Because remember, r has to be a positive remainder. So we don't use negative 13, we use negative 15. So negative 54 is equal to 4 times negative 14, then plus 2. Right? So 4 times negative 14 would be negative 56. Add 2 gives us the negative 54. So our q would be negative 14, and our r would be 2. Now let's look at 54 for n and 70 for d. Well, since 54 is less than 70, our q would have to be 0. And of course, then our remainder would be 54. So in this case, our q is equal to 0, and our r is equal to 54. So we look at another consequence of integers. It's called the parity property. So the parity of an integer simply refers to whether the integer is even or odd. So for example, 5 has odd parity, whereas 28 has even parity. And the parity property states that an integer is either even or odd. So every integer has to be one of these two options. So we're going to go ahead and prove the parity property. So let n be an integer. We must show that n is either even or odd. But the Quotient-Remainder Theorem states that there exist integers q and r such that n is 2q plus r, and 0 is less than equal to r, which is less than 2. However, the only integers that satisfy this inequality are 0 and 1. So n must either be written in the form of 2q plus 0 or 2q plus 1. In this former case, n is just 2q, which means that n would be even. Right? In this latter case, n is 2q plus 1, which means n is odd. Now, these are the only two possibilities for n, and so n must be either even or odd. Now, we will go ahead and prove that any two consecutive integers have opposite parity. That is, if you have an even integer, you know that the next integer would be odd. And then the integer after that odd one would be even again. So let m be an integer that is given. Then the next consecutive integer would simply be n plus 1. We now want to show that one is even and the other is odd. So by parity property, n is either even or odd. So this proof must be broken into two parts. We will first assume that n is even, and of course have to show that n plus 1 is odd. Then we will assume that n is odd, and show that n plus 1 is even. So first suppose that n is even. Then by definition, we have to have an integer q such that m is equal to 2q. So the next consecutive integer would be m plus 1, which is 2q, because that's what n is, right, up here, plus 1, which is 2q plus 1, which is the definition of odd. So m plus 1 is odd. Next, let's assume that m is odd. Then, by definition, there has to be an integer q such that m is 2q plus 1. So the next consecutive integer would be m plus 1, which is this quantity of 2q plus 1, which is 2q plus 2. We can factor out that 2, and we have q plus 2. Now, q plus 2 is an integer, right? Because it is the sum of two integers. So we can write n plus 1 as 2 times an integer r, which means, by definition, n is even. Therefore, any two consecutive integers must have opposite parity, which is what we wanted to prove and show the proof is complete. So this is now the second time we've looked at a proof by division into cases. So the method for this proof is fairly straightforward. It's used to prove a statement of the form if a1 or a2 or a3 yada 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 or an, then c, then what we have to do is we have to prove all the following. If a1 then c, if a2 then c, if a3 then c, so on and so forth, if an then c. What this does is it proves that regardless of which case is true, because remember, for a disjunction to be true, you need only one to be true. So if you can show that no matter which case you assume is true leads logically to C, then we've shown that C is true regardless of which of the A's happens to be the case. So to do division cases, as we've seen, you start with assuming A1 is true and you show that C is true. Then you're going to go, okay, well now assume that A2 is true and show that C is true, and so on and so forth. So another example of division into cases, the square of any odd integer has the form 8m plus 1 for some integer m. Well, in a previous proof, we showed that integer is of the form 2q or 2q plus 1. So if we assume that m is an odd integer and use m is 2q plus 1, it's not going to work. So through work, we can show that we need to start with the divisor of 4. We let n be an integer that is odd. What we want to show is n squared is 8m plus 1 for some integer n. So by the quotient-remainder theorem, we can represent n in one of 4 ways, either as 4q, q plus 1, 4q plus 2, or 4q plus 3 for some integer q. Now, both 4q and 4q plus 2 are even. So we represent n as either 4q plus 1 or 4q plus 3. And so our proof will be divided into 2 cases. One where n is 4q plus 1, and the second where n is 4q plus 3. So suppose first that n is 4q plus 1 for some integer q. Then n squared would be the quantity of 4q plus 1 squared, which would be 16 squared plus 8q plus 1. We can factor an 8 out of these first 2 terms. So we have 8 is equal to 2q squared plus q, and then all that's plus 1. Now, 2q squared plus q is an integer, right? Because it is the sum and product of integers. So this means that we just wrote n squared as 8 times an integer m plus 1, which was to be shown. If we now suppose that n is 4q plus 3 for some integer q, then n squared, the quantity 4q plus 3 squared, which is 16q squared plus 24q plus 9, which we can write as 16q squared plus 24q plus 8 plus 1. Now from these first 3 terms, we factor out an 8 to be left with 2q squared plus 3q plus 1, and then all that is plus 1. But this term here, this 2q squared plus 3q plus 1, is an integer. And so we've now written n squared is 8 times an integer m plus 1, which was to be shown. So in both cases, we've shown that we can write n squared as times an integer plus 1. And so the square of any odd integer has the form 8m plus 1 for some integer n. And the proof is complete. So in this lesson, we looked at divisibility, quotient-remainder theorem, and then learned a new technique of proof known as division into cases. And so that concludes our study of divisibility.